The RBMK reactor at Chernobyl Unit 4 represented a fundamentally different design philosophy from Western pressurized water reactors, where PWRs prioritized containment and negative feedback coefficients. RBMKs emphasized operational flexibility and fuel economy. This analysis examines how the RBMK's unique design features, graphite moderation, pressure tube channels, and positive void coefficients, created operational advantages that masked inherent vulnerabilities. When operators conducted a routine turbogenerator coast-down test on April 26, 1986, they followed established procedures within a reactor design that had operated successfully for over a decade. Yet specific design characteristics, combined with an unusual power history and control rod configuration, created conditions where normal operational responses amplified rather than mitigated the developing transient. At 1:23:04 on April 26, 1986, operators at Chernobyl Nuclear Power Plant Unit 4 initiated a planned turbogenerator coast-down test. The RBMK 1000 reactor was operating at 200 megawatts thermal power. All control systems functioned normally. Emergency protection system indicators showed green. Main circulation pumps maintained adequate flow rates through 1,661 individual fuel channels. The test proceeded according to documented procedures. When turbogenerator TG8 was disconnected from the electrical grid, its spinning mass continued to drive the main circulation pumps as designed, providing crucial seconds of cooling flow during the transition to backup power. This was exactly the safety margin the test was meant to verify. Yet within 40 seconds, operators would press the emergency shutdown button AZ5, not because anything appeared wrong with the reactor, but because power began rising unexpectedly. The control rods began their descent into the core at their normal speed of 0.4 meters per second. Then they stopped halfway down, jammed in their channels by core geometry that had fundamentally changed. The reactor's destruction was not caused by the test itself, nor by operator error, nor by a single component failure. It resulted from a design philosophy that prioritized operational flexibility over inherent safety margins, combined with a control rod design that introduced positive reactivity precisely when negative reactivity was most needed. How could an emergency safety system designed to shut down a reactor instead trigger its destruction? At 1:23:04 on April 26, 1986, operators at Chernobyl Nuclear Power Plant Unit 4 initiated a planned turbogenerator coast-down test. The RBMK 1000 reactor was operating at 200 megawatts thermal power. All control systems functioned normally. Emergency protection system indicators showed green. Main circulation pumps maintained adequate flow rates through 1,661 individual fuel channels. The test proceeded according to documented procedures. When turbogenerator TG8 was disconnected from the electrical grid, its spinning mass continued to drive the main circulation pumps as designed, providing crucial seconds of cooling flow during the transition to backup power. This was exactly the safety margin the test was meant to verify. Yet within 40 seconds, operators would press the emergency shutdown button AZ5, not because anything appeared wrong with the reactor, but because power began rising unexpectedly. The control rods began their descent into the core at their normal speed of 0.4 meters per second. Then they stopped halfway down, jammed in their channels by core geometry that had fundamentally changed. The reactor's destruction was not caused by the test itself, nor by operator error, nor by a single component failure. It resulted from a design philosophy that prioritized operational flexibility over inherent safety margins, combined with a control rod design that introduced positive reactivity precisely when negative reactivity was most needed. How could an emergency safety system designed to shut down a reactor instead trigger its destruction? The RBMK reactor represented a fundamentally different approach to nuclear power generation than the pressurized water reactors dominating Western nuclear programs. Where PWR designers emphasized negative feedback coefficients and robust containment structures, RBMK engineers prioritized fuel economy, operational flexibility, and the ability to refuel during operation. This design philosophy emerged directly from the reactor's origins in Soviet plutonium production facilities, where operational flexibility and uranium utilization efficiency took precedence over passive safety characteristics. The RBMK's core design embodied these priorities through its unique combination of graphite moderation and water cooling in individual pressure tubes. Unlike PWRs, where fuel assemblies sit in a large pressure vessel filled with water that serves both as coolant and neutron moderator, the RBMK separated these functions. Graphite blocks provided neutron moderation while water flowing through individual zirconium pressure tubes removed heat from fuel assemblies. This channel-type design enabled online refueling and eliminated the need for massive pressure vessels that Soviet industry struggled to manufacture reliably. According to the technical documentation provided to the IAEA post-accident review meeting, the RBMK 1000 core consisted of 1,700 tons of graphite arranged in a cylindrical stack 11.8 meters in diameter and 7 meters high. Within this graphite moderator, 1,661 fuel channels contained uranium dioxide fuel enriched to 2% U-235. Each fuel channel held 2 fuel assemblies, one above the other, with each assembly containing 18 fuel rods of 13.6 mm diameter enclosed in zirconium cladding. This design provided genuine advantages over contemporary reactor types. The large thermal mass of the graphite moderator created inherent stability during normal operations. The individual fuel channels enabled precise local power control and simplified fuel handling compared to opening an entire pressure vessel. Most significantly for Soviet planners, the design maximized uranium utilization while requiring only materials and manufacturing capabilities available within the Soviet Union. However, these advantages came with physics trade-offs that created fundamental safety vulnerabilities. The separation of moderation and cooling functions meant that voiding of coolant water could increase reactivity rather than decrease it, as occurred in PWRs. Under normal operating conditions with adequate control rod insertion, this positive void coefficient remained manageable. But specific combinations of power level, control rod configuration, and coolant conditions could create situations where losing coolant water increased neutron multiplication rather than providing the negative reactivity essential for safe shutdown. The most critical design characteristic lay in the emergency protection system itself. The control and protection system consisted of 211 absorbing rods categorized into 4 functional groups: 24 shortened absorbing rods for axial power distribution control, 139 rods for manual radial power distribution regulation, 24 rods for automatic power control, and 24 emergency rods. The rods designed for regulation and emergency shutdown incorporated a feature that would prove fatal: graphite displacers. These graphite displacers, each 4.5 meters long in rods with total length of 5.12 meters, served a legitimate design purpose. When control rods were withdrawn to their upper limit positions, the graphite displacers remained within the active core region, displacing water that would otherwise absorb neutrons unproductively. This arrangement significantly improved the reactor's neutron economy, enabling higher fuel burnup and better uranium utilization. Critical objectives for Soviet nuclear strategy. But the graphite displacer design created a fundamental contradiction within the emergency protection logic. When control rods were fully withdrawn above the core, water columns 1.25 meters high formed both above and below each displacer. Inserting rods from this position initially displaced water from the bottom of fuel channels, replacing it with graphite that absorbed fewer neutrons than water. During the first few seconds of rod insertion, this displacement introduced positive reactivity into the lower portion of the core, exactly opposite to the negative reactivity required for emergency shutdown. Soviet reactor designers were aware of this effect, termed the positive reactivity surge in technical documentation. However, their understanding remained incomplete. Internal documents from the chief designer organization suggested the phenomenon occurred only with neutron flux distributions disturbed downwards, when in fact it could manifest under various flux patterns. This misunderstanding reflected deeper analytical limitations, stemming from the computational tools available during RBMK development in the 1960s. The reactor physics codes available to Soviet designers lacked the capability to model three-dimensional neutronics coupled with thermal hydraulics under transient conditions. Most safety analyses relied on simplified one-dimensional models that could not capture the spatial coupling between void formation, neutron flux distribution, and control rod effectiveness. These analytical limitations meant designers could not fully predict reactor behavior under the complex conditions that would develop during the April 26 test. Operational procedures attempted to manage these physics characteristics through administrative controls. Technical specifications required maintaining the operational reactivity margin, the total reactivity worth of control rods inserted in the core, above specified limits. For Units 3 and 4 at Chernobyl, this limit was 30 equivalent control rods under normal operating conditions. However, calculating ORM required complex computations involving the position and effectiveness of all 211 control rods, taking 7 to 10 minutes even with computer assistance. This computational complexity created a critical gap between design intent and operational reality. While technical specifications mandated ORM monitoring, the measurement system made continuous compliance verification impractical during dynamic operations. Operators focused primarily on power control and immediate safety parameters that could be assessed quickly, while reactivity margins, the fundamental measure of safety reserve, remained largely invisible in real-time operations. Training programs reflected and reinforced this operational focus. Operator training emphasized power control, flow balancing, and system response to common transients, like pump trips or turbine shutdowns. While reactor physics principles were covered in initial training, ongoing qualification focused on systems operations rather than reactivity management. This training philosophy was logical given normal operating requirements, but left operators poorly prepared to recognize situations where physics considerations should override immediate operational objectives. The RBMK's positive void coefficient created another operational challenge largely absent from PWR operations. In pressurized water reactors, coolant heating or voiding introduces negative reactivity that automatically opposes power increases, providing inherent stability. The RBMK's positive void coefficient under certain conditions meant that power increases could become self-reinforcing rather than self-limiting, while automatic control systems compensated for this characteristic during normal operations. Transient conditions could overwhelm these protections. Experimental studies conducted in the late 1970s had quantified the magnitude of this challenge. With reduced numbers of additional absorbing rods in the core and increased fuel burnup, the void coefficient could reach 5 times the effective delayed neutron fraction, 5 BDAF, reducing the power stabilization time constant to approximately 3 minutes. These findings prompted development of a local automatic control system designed to prevent uncontrolled power excursions. But the underlying physics vulnerability remained. The solution to the positive void coefficient problem was technically straightforward but economically costly. Maintaining sufficient additional absorbing rods permanently in the core and increasing fuel enrichment from 2 to 2.4% could reduce the void coefficient below 1 BTAF, providing inherent stability similar to PWRs. However, these measures would significantly increase fuel cycle costs and reduce the competitive advantage that made RBMKs attractive to Soviet planners. Economic considerations therefore delayed implementation of these modifications until after the Chernobyl accident. Perhaps most significantly, the RBMK design reflected a different philosophical approach to nuclear safety than emerging Western practices. While Western designers increasingly emphasized passive safety features and defense in depth through multiple independent barriers, RBMK designers relied primarily on active systems and administrative controls. This approach assumed competent operators working within well-defined procedures could manage the reactor's characteristics safely. The design provided numerous control mechanisms and monitoring systems, but depended heavily on operator knowledge and decision-making to maintain safety margins. This design philosophy was not inherently flawed. Many complex industrial systems operate safely under operator control. However, it required exceptional attention to human factors engineering, procedure development, and training effectiveness. The control room interface needed to provide operators with clear, unambiguous information about reactor state and safety margins. Procedures needed to account for the reactor's unique characteristics and potential failure modes. Training needed to prepare operators for the specific challenges of RBMK operations rather than generic reactor principles. Evidence suggests these human factors considerations received insufficient attention during RBMK development. Control room displays emphasized immediate operational parameters, power, flow, temperatures, pressures, rather than underlying safety margins like reactivity balance and spatial power distribution. Procedures were structured around normal evolutions and common malfunctions rather than the reactor's specific physics vulnerabilities. Training focused on system operations rather than the reactor theory knowledge required to understand why certain actions could be dangerous even when they achieved immediate operational objectives. The cumulative effect of these design decisions created a reactor that operated safely under normal conditions but contained latent vulnerabilities that could be activated by specific combinations of operational states. The reactor could appear completely normal on all instrumentation while approaching conditions where standard safety systems would not function as designed. Operators could follow approved procedures and still unknowingly degrade fundamental safety margins. Most critically, the emergency protection system could introduce positive reactivity under precisely the conditions where operators would be most likely to activate it, during unexpected power increases. These characteristics did not make accident inevitable, but they created a system where multiple independent failures could align to defeat the defense-in-depth philosophy underlying nuclear safety. Normal organizational pressures to maintain schedule and power output could gradually degrade safety margins without triggering clear warning indicators. Routine test procedures could create plant conditions where design vulnerabilities became active threats. Standard emergency responses could amplify problems rather than mitigating them. Understanding these design characteristics provides essential context for analyzing the events of April 26, 1986. The operators who conducted the turbo generator coast-down test were working within a reactor design that rewarded operational flexibility and power production efficiency over passive safety characteristics. Their training prepared them to manage normal operations and respond to familiar transients, but not to recognize the specific physics conditions that would make their reactor uniquely vulnerable. The procedures they followed had been developed based on incomplete understanding of the reactor's behavior under boundary conditions. When they activated the emergency protection system, they were following training and procedures that had been successful in previous applications. The Chernobyl accident was not caused by a single design flaw or operator error, but by the interaction between design characteristics that created hidden vulnerabilities, operational practices that could activate those vulnerabilities, and emergency systems that could amplify, rather than mitigate the resulting problems. This interaction was not random, but emerged systematically from the design philosophy and development process that created the RBMK. The specific technical failures of April 26 became possible only within this broader context of design assumptions that prioritized different objectives than the defense-in-depth principles that would later become standard in nuclear safety. The systematic degradation of safety margins that enabled the Chernobyl accident began not on April 26, 1986, but months earlier, through a series of individually reasonable decisions that collectively created dangerous operational conditions. Understanding how Reactor Unit 4 reached a state where routine procedures could trigger catastrophic failure requires examining the latent organizational and technical conditions that accumulated over time, creating what safety theorist James Reason would later term resident pathogens within the system. The most critical latent condition involved the practical impossibility of maintaining real-time awareness of the reactor's fundamental safety parameter, the operational reactivity margin. According to the State Committee for Atomic Safety Survey's 1991 investigation, ORM represented the total reactivity worth of control rods inserted in the core, measured in equivalent fully inserted rods. This parameter directly determined the reactor's ability to shut down safely and controlled the magnitude of the positive, void coefficient that made RBMKs potentially unstable. Technical specifications for Chernobyl Units 3 and 4 required maintaining ORM above 30 equivalent rods during power operations above 700 megawatts thermal. Below this threshold, the positive void coefficient could become large enough to make power control difficult and emergency shutdown potentially ineffective. However, calculating ORM required determining the precise position and effectiveness of all 211 control rods in the core, accounting for local neutron flux conditions, fuel burnup, and xenon concentration. Even with computer assistance, this calculation required 7 to 10 minutes to complete, an eternity, during dynamic plant operations. This computational complexity created a fundamental mismatch between design requirements and operational reality. While ORM represented the most important single parameter for reactor safety, operators could not monitor it continuously during transients. Instead, they relied on indirect indicators, control rod positions, reactor power, and neutron flux measurements that provided incomplete information about reactivity balance. The control room computer system could calculate ORM periodically, but operators often proceeded with operational decisions without waiting for updated calculations. The complexity of ORM assessment reflected deeper limitations in the reactor monitoring systems available to operators. Unlike modern digital systems that can continuously calculate and display derived parameters, the analog instrumentation systems of the 1980s required operators to mentally integrate multiple readings to assess reactor state. Critical safety parameters like spatial power distribution, reactivity coefficients, and shutdown margin existed as computational abstractions rather than directly observable quantities. Training programs attempted to compensate for these limitations by teaching operators to recognize patterns in observable parameters that indicated approaching problems. However, this pattern recognition approach proved inadequate for the specific conditions that would develop during the April test. The unusual power history and control rod configuration created a reactivity state that had not been encountered during normal operations or covered explicitly in training scenarios. Documentation from the Chernobyl Training Center reveals that reactor physics training emphasized general principles rather than specific operational limits. Operators learned that maintaining adequate control rod insertion was important for reactor control, but received limited training on recognizing situations where standard operational practices might violate ORM requirements. The focus remained on immediate operational parameters, power, temperature, flow, rather than the underlying physics that determined whether those parameters could be maintained safely. This training approach reflected broader organizational priorities that emphasized power production reliability over conservative safety margins. Soviet nuclear plants operated under intense pressure to meet electrical generation targets, with plant management evaluated primarily on capacity factor and availability. While safety was officially the highest priority, the performance measurement system created incentives to maintain operation whenever possible rather than shutting down for conservative safety reasons. The organizational pressure to maintain operation created a systematic bias toward interpreting ambiguous situations optimistically. When ORM calculations were delayed or incomplete, the tendency was to continue operations rather than shut down pending verification of safety margins. When unusual conditions developed, operators sought ways to stabilize the reactor at power rather than immediately implementing conservative shutdown procedures. This bias was not unique to Soviet plants, but reflected universal human tendencies that safety-critical industries must actively counteract through procedures and training. The specific sequence of events that degraded safety margins at Unit 4 began on April 25, 1986, when the reactor was scheduled for shutdown for routine maintenance. Before shutdown, plant personnel planned to conduct a safety system test that had been postponed from previous outages. The test was designed to verify that the turbo generator's rotational inertia could provide sufficient electrical power to operate reactor coolant pumps during the transition to backup power sources following a station blackout. This test objective was technically sound and safety relevant. Station blackout scenarios represented credible threats to reactor safety, and demonstrating adequate coolant pump operation during the transition to emergency power could verify important safety margins. However, the test procedure required operating the reactor at reduced power levels, where the positive void coefficient was larger and control rod effectiveness was reduced, precisely the conditions where ORM requirements became most critical. The test procedure specified conducting the experiment at 700 to 1000 MW thermal power, a level where adequate ORM could typically be maintained with proper control rod management. However, the procedure did not explicitly require verifying ORM before test initiation, nor did it provide specific guidance for terminating the test if ORM fell below safe limits. This procedural gap reflected the broader pattern of focusing on immediate operational objectives rather than fundamental safety parameters. Initial power reduction proceeded normally on April 25, with reactor power decreasing from nominal 3,200 megawatts thermal to the target range. However, at 14 hours, the Kyiv electrical grid dispatcher requested delaying the shutdown to compensate for an unexpected loss of generation elsewhere in the system. This request created the first critical decision point, where organizational pressures began to override conservative safety practices. Plant management approved the delay despite having already begun test preparations, including disconnecting the emergency core cooling system as specified in the test procedure. This decision placed the reactor in an unusual configuration, reduced power with safety systems disabled, for an extended period not anticipated in the original procedure. The delay also meant that a different operating crew would conduct the test than had been originally planned and trained for this specific evolution. When power reduction resumed at 23:10 on April 25, the reactor's condition had changed significantly from the initial test configuration. Extended operation at intermediate power levels had allowed xenon-135, a strong neutron poison, to accumulate in the fuel. Xenon-135 is produced both directly from fission and as a decay product of iodine-135, but it also absorbs neutrons and decays with a 9.2-hour half-life. The concentration reaches equilibrium during steady-state operation, but can vary dramatically during power changes. During the planned power reduction, xenon concentration initially remained at the level appropriate for high-power operation. As reactor power decreased, xenon production from direct fission decreased immediately, but production from iodine decay continued at the higher rate established during previous high-power operation. Simultaneously, the neutron flux reduction decreased the rate of xenon removal through neutron absorption. These competing effects caused xenon concentration to increase rapidly, absorbing reactivity that had to be compensated by withdrawing control rods. The xenon transient created a reactivity management challenge that was well understood in principle but difficult to manage in practice. Standard procedures called for withdrawing control rods gradually to compensate for xenon buildup, but this process had to be balanced against maintaining adequate shutdown margin. If too many rods were withdrawn too quickly, the reactor could become vulnerable to power excursions when xenon eventually decayed. If insufficient rods were withdrawn, the reactor might shut down automatically as xenon continued to build. At 0:28 on April 26, automatic control systems allowed reactor power to fall to approximately 30 megawatts thermal, far below the intended test power level, and well into the range where xenon effects dominated reactivity balance. This power level created several problems simultaneously: enhanced xenon poisoning that required extensive control rod withdrawal to overcome, reduced cooling flow that increased void formation potential, and decreased delayed neutron effectiveness that reduced the time available for operator response to power changes. The shift supervisor, Alexander Akimov, and senior reactor control engineer, Leonid Toptunov, initially attempted to shut down the reactor in response to this unexpected power reduction. However, Deputy Chief Engineer Anatoly Dyatlov overruled this decision and ordered them to restore power for the test. This decision reflected the organizational pressure to complete scheduled work rather than accepting conservative delays, but it also created the conditions that would prove fatal. Restoring power from the 30 megawatts level required withdrawing virtually all control rods from the core to overcome xenon poisoning. By 1, operators had withdrawn all but 6 to 8 control rods, reducing the ORM to approximately 1/4 of the minimum specified in technical specifications. However, calculating the precise ORM value would have required stopping operations for several minutes, time that seemed unavailable given the pressure to complete the test before the scheduled maintenance outage. The reduced ORM created several cascading vulnerabilities. With minimal control rod insertion, the positive void coefficient increased significantly, making the reactor more sensitive to cooling system disturbances. The spatial power distribution became distorted, with power concentrated in regions of the core with the least neutron absorption. Most critically, the emergency protection system's effectiveness decreased substantially, as most control rods were already withdrawn to positions where their initial insertion would introduce positive rather than negative reactivity. Operators were aware that control rod insertion had been reduced to enable power restoration, but they lacked clear guidance on the specific safety implications. The connection between ORM and emergency shutdown effectiveness was not emphasized in training, and the control room displays did not provide real-time indication of how close the reactor was to configurations where SCRAM could be ineffective. The reactor appeared normal on all immediate indicators while existing in a state where standard safety systems could not function as designed. To provide adequate cooling for the planned test, operators activated 8 main circulation pumps, more than typically required for the power level but necessary to ensure adequate flow during the turbogenerator coast-down phase. This enhanced cooling flow created additional complications by reducing steam void formation in fuel channels. While improved cooling might seem beneficial, it also increased the potential for rapid void formation if flow were suddenly reduced, and it masked the reactor's proximity to thermal hydraulic instabilities. The combination of low power, minimal control rod insertion, and high coolant flow created a reactor condition that was stable in the immediate term but contained multiple pathways to rapid instability. Small changes in reactivity, flow, or temperature could trigger positive feedback loops that would overwhelm the remaining control authority. The reactor existed in what control theorists term a brittle state, apparently normal but vulnerable to rapid transitions to dangerous conditions. Perhaps most significantly, the cumulative effect of decisions made to enable the test had systematically removed the defense-in-depth protections that normally prevented accidents. Administrative controls on ORM had been violated to overcome xenon transients. The emergency core cooling system had been disabled per test procedures. Control rod effectiveness had been minimized by operational requirements. Reactor conditions had been pushed toward limits where normal feedback mechanisms became unreliable. Each individual decision had seemed reasonable given immediate operational pressures and available information. Delaying shutdown to support grid stability was a legitimate operational request. Overcoming xenon poisoning through control rod withdrawal was standard practice. Disabling ECCs for testing was explicitly authorized in approved procedures. Operating additional circulation pumps provided conservative cooling margins. None of these actions appeared dangerous in isolation, and all had been accomplished successfully in previous operations. However, the combination of these individually reasonable decisions created system conditions that had never been fully analyzed or experienced. The reactor's behavior under such extreme conditions was not well understood, because the computational tools available during design could not model the complex interactions between spatial neutronics, thermal hydraulics, and control system response. Operators were managing a reactor in a configuration that existed beyond the boundaries of validated analysis and operational experience. The broader organizational context that enabled this situation reflected systemic weaknesses in how nuclear safety was understood and managed in the Soviet system. The emphasis on meeting production targets created pressure to continue operations even when conservative practice would suggest shutdown. The compartmentalization of technical information meant that operators understood their immediate responsibilities, but not necessarily how their actions affected overall safety margins. The focus on procedural compliance, rather than underlying safety principles, left operators unprepared for situations where following procedures could create, rather than prevent dangerous conditions. These organizational factors were not unique to the Soviet nuclear program, but reflected broader challenges in managing complex, tightly coupled technical systems under production pressure. Similar organizational influences have contributed to major accidents across many industries, from chemical plants to aviation to space systems. The Chernobyl case provides a particularly clear example of how latent organizational weaknesses can accumulate over time to create conditions where normal operations become unexpectedly hazardous. By 1:22 on April 26, all of these latent conditions had aligned to create a reactor system that appeared normal to operators but existed in a state where routine safety actions could trigger catastrophic failure. The stage was set for an initiating event that would activate vulnerabilities that had been developing for hours through the accumulation of individually reasonable but collectively dangerous decisions. At 1:23:04 on April 26, 1986, Senior Reactor Control Engineer Leonid Toptunov closed the emergency regulating valves to turbogenerator TG-8, officially beginning the turbogenerator coast-down test that would destroy Chernobyl Unit 4. The test procedure called for measuring how long the spinning turbogenerator could continue powering the main circulation pumps after steam supply was cut off, simulating conditions during a station blackout when backup diesel generators were starting up. The test objective represented sound safety engineering. Station blackout scenarios, simultaneous loss of off-site power and on-site emergency power, posed credible threats to reactor safety at nuclear plants worldwide. During such events, maintaining adequate reactor coolant flow during the transition to emergency power could mean the difference between safe shutdown and core damage. The coast-down test was designed to measure whether the turbogenerator's rotational inertia could bridge this critical gap, providing essential safety margin verification. From the operator's perspective in the Unit 4 control room, the test initiation appeared routine. Reactor power had been stabilized at approximately 200 megawatts thermal, higher than originally planned due to the xenon transient, but within acceptable bounds for conducting the test. All 8 main circulation pumps were operating, providing conservative cooling flow. Steam generator water levels were normal. Primary circuit pressure remained stable at approximately 7 MPa. The reactor appeared to be responding normally to control inputs, with automatic systems maintaining stable conditions. The test procedure itself was methodical and conservative. Upon closing the turbine valves, operators would monitor how electrical frequency and voltage from the coasting turbogenerator decreased over time, while measuring the corresponding reduction in main circulation pump speed and flow. The test would continue until pump performance dropped below acceptable limits, at which point backup electrical supplies would be connected to maintain adequate cooling. Emergency diesel generators remained available throughout the test, providing additional backup if needed. However, beneath these apparently normal surface conditions, the reactor existed in a state that was unprecedented in operational experience and poorly understood by available analytical methods. The combination of low power, minimal control rod insertion, and high coolant flow had created thermal hydraulic conditions that were not explicitly covered in design analyses or training scenarios. The reactor's behavior under these conditions could not be predicted reliably using the analytical tools available in 1986. The first indication that reality was diverging from expectations came not from reactor instrumentation, but from the turbogenerator performance itself. As TG-8 began to coast down following steam supply closure, its electrical output decreased more rapidly than anticipated in previous similar tests. The frequency dropped from 50 Hz toward the 45 Hz threshold, at which protective systems would automatically disconnect electrical loads to prevent equipment damage. This faster than expected coast down reduced the time available for pump flow transition and created additional time pressure for operators managing the test. More significantly, the electrical transient affected the main circulation pumps in ways that were not fully anticipated in test planning. As voltage and frequency decreased, pump performance degraded non-linearly, causing flow reductions that were larger and occurred sooner than expected. According to post-accident analysis by Checharov, the main circulation pumps contained internal protection systems that would disconnect them automatically if voltage fell below 75% of nominal or if frequency remained below 45, for more than specified time periods. This pump protection feature created a potential failure mode that was not explicitly addressed in test procedures. If the electrical transient from the coasting turbogenerator triggered automatic pump disconnection, coolant flow could drop suddenly rather than gradually, creating conditions for rapid void formation in fuel channels. Given the reactor's current state with minimal control rod insertion and elevated void coefficient, such flow reductions could trigger positive reactivity insertion that might exceed the control system's ability to compensate. The flow reduction began approximately 36 seconds after test initiation, as pump performance degraded with decreasing electrical supply quality. Neutron flux monitoring systems began indicating increasing power in the lower portion of the core, suggesting that void formation was beginning to affect neutron moderation. However, these indications were subtle and developed gradually, not triggering immediate alarm responses that would clearly indicate developing problems. From the operator's perspective, the initial stages of the test appeared successful. The turbogenerator was performing as expected, providing electrical power to essential pumps during the coast-down phase. Reactor power remained controllable through automatic systems, with no dramatic changes in key parameters. Temperature and pressure readings remained within normal ranges. The test was proceeding according to procedure, and operators had no clear indication that fundamental reactor physics conditions were changing in ways that could not be reversed. However, the reactor's internal state was changing in ways that were not visible on standard instrumentation. As coolant flow decreased and localized void formation began in individual fuel channels, neutron moderation characteristics shifted subtly but significantly. The reduced water density in voided regions allowed more neutrons to reach thermal energies where they were more likely to cause fission in uranium-2 and 35, slightly increasing reactivity in affected core regions. This reactivity increase was initially small and localized, easily compensated by automatic control systems that inserted control rods slightly to maintain stable power. However, the compensation process consumed some of the remaining control rod insertion that provided safety margin for emergency shutdown. Each small adjustment further reduced the already minimal operational reactivity margin, moving the reactor incrementally closer to configurations where emergency protection systems could not function effectively. The spatial distribution of void formation created additional complications that were not captured by average core measurements. Individual fuel channels throughout the core experienced different flow rates due to manufacturing tolerances, thermal conditions, and hydraulic resistance variations. As overall flow decreased during the test, channels with higher thermal output or lower flow resistance began forming steam bubbles first, creating localized reactivity increases that had to be compensated by control rod adjustments. This spatial coupling between thermal hydraulics and neutronics represented one of the most challenging aspects of RBMK analysis that existing computational tools could not model adequately. The reactor's behavior depended not just on average core conditions, but on the detailed distribution of void formation, neutron flux, and control rod effectiveness throughout the 1,661 individual fuel channels. Small changes in one region could affect neighboring regions through neutron diffusion, creating complex feedback loops that were difficult to predict or control. As the test progressed, these spatial effects began to manifest as observable changes in neutron flux distribution. Local power monitoring systems indicated power increases in specific core regions, while average power remained stable. This pattern suggested that reactivity redistribution was occurring, but the implications were not immediately clear to operators focused on overall reactor control rather than detailed spatial analysis. The automatic control systems responded to these localized power increases by inserting additional control rods to maintain overall reactor stability. However, each control rod insertion further reduced the available shutdown margin, moving the reactor closer to conditions where the emergency protection system's graphite displacers could introduce net positive reactivity rather than the negative reactivity required for safe shutdown. At 1:23:40, operators observed a clear indication that reactor conditions were changing beyond the envelope of normal test experience. Neutron flux monitoring began showing sustained power increases that could not be controlled through normal automatic adjustments. The reactor period, the time required for power to increase by a factor of E, began shortening noticeably, indicating that reactivity was increasing faster than control systems could compensate. This power increase represented the crossing of a critical threshold where the reactor's physics, characteristics, fundamentally changed. The combination of void formation from reduced cooling flow and minimal control rod insertion had created conditions where small perturbations could trigger positive feedback loops. Void formation increased reactivity, which increased power, which increased heating, which caused additional void formation. The automatic control systems that normally dampened such oscillations had insufficient control authority to break this cycle. The operator's response to these indications followed their training and the reactor's standard emergency procedures. Recognizing that power was increasing beyond normal control authority and that the test conditions were no longer stable, Shift Supervisor Alexander Akimov ordered the activation of the emergency protection system. Senior Reactor Control Engineer Leonid Toptunov pressed the AZ-5 button at 1:23:40, initiating the emergency shutdown sequence that was designed to insert all control and protection rods into the core. From the operator's perspective, this decision represented appropriate conservative response to unexpected conditions. The test was not proceeding as planned, reactor power was increasing unexpectedly, and standard control methods were proving inadequate. Activating emergency protection was exactly the response prescribed by training and procedures for situations where normal control authority was insufficient. The decision was made promptly, without hesitation, following established protocols for responding to off-normal conditions. However, the reactor's actual configuration meant that emergency protection would have consequences opposite to those intended by designers and expected by operators. With most control rods already withdrawn to overcome xenon poisoning, their insertion from upper limit positions would initially displace water from the bottom of fuel channels, introducing positive reactivity precisely when negative reactivity was most needed. The emergency protection system that was designed to guarantee reactor shutdown would instead guarantee reactor destruction. This contradiction between design intent and actual reactor physics represented the culmination of the latent conditions and design vulnerabilities that had been accumulating since the test planning began. The reactor existed in a configuration that appeared normal to operators, but was fundamentally different from the conditions assumed in design analyses and covered in training. The emergency protection system was being activated under precisely the circumstances where its design characteristics would prove catastrophically inadequate. The activation of AZ-5 represented the point of no return, where recovery became impossible regardless of subsequent operator actions. The graphite displacers in the descending control rods would introduce positive reactivity that exceeded any possible compensation mechanisms. The reactor period would shorten to seconds, then milliseconds, creating power levels that would destroy fuel geometry faster than any control system could respond. The emergency protection system designed to provide the ultimate safety backup would instead provide the mechanism for ultimate destruction. At 1:23:40, as Toptunov's hand pressed the AZ-5 button, the operators believed they were taking decisive action to protect their reactor and their plant. They had followed procedures, responded appropriately to unexpected conditions, and activated the systems specifically designed for emergency situations. They had acted competently within their training and understanding of reactor operations. Their actions were logical, justified, and completely consistent with established safety practices. Yet they had also initiated a sequence of events that would destroy their reactor within seconds and create the worst accident in the history of commercial nuclear power. This contradiction was not the result of operator error or procedural violations, but emerged from fundamental characteristics of the reactor design interacting with operational conditions that had never been fully analyzed or anticipated. The divergence between appearance and reality had reached the point where correct responses based on normal understanding would produce catastrophically incorrect outcomes. The AZ-5 activation represented more than just an unsuccessful emergency response. It demonstrated how complex technical systems can create situations where expertise and training become counterproductive. The operator's knowledge and experience, developed through years of successful reactor operation, led them to actions that were appropriate for normal reactor configurations, but devastating for their actual situation. The very systems and procedures designed to prevent accidents had become the mechanisms through which accidents would occur. At 1:23:40, when Leonid Toptunov pressed the AZ-5 button to initiate emergency reactor shutdown, he activated a sequence of events that had been precisely engineered to guarantee reactor safety under all credible operating conditions. The emergency protection system represented the ultimate defense against reactor accidents, designed with redundancy and conservatism that should have made failure virtually impossible. Within the next 4 seconds, this system would instead provide the mechanism for the reactor's complete destruction. The emergency protection system's response to AZ-5 activation followed its design specifications exactly. Electromagnetic clutches released simultaneously on all 211 control and protection system rods throughout the reactor core. The rods began falling under gravity toward their fully inserted positions, with their descent controlled by hydraulic dashpots to prevent mechanical damage from excessive insertion speeds. The system was designed to achieve full rod insertion within 18 to 20 seconds, providing negative reactivity insertion at a rate of approximately 0.4 meters per second. Under normal operating conditions, this response would have promptly and safely shut down the reactor. The control rods contained boron carbide absorber sections specifically designed to capture neutrons and halt the fission chain reaction. Even if the reactor were operating at full power with maximum reactivity requirements, the emergency protection system contained sufficient negative reactivity to guarantee shutdown with substantial margin. The system had performed successfully in previous tests and had never failed to shut down an RBMK reactor when activated. However, the reactor's current configuration differed fundamentally from the normal operating conditions assumed in emergency protection system design. Most critically, the vast majority of control rods had been withdrawn to their upper limit positions to compensate for xenon poisoning, placing their graphite displacers at the midpoint of the active core rather than in their normal positions, partially inserted into the fuel region. This rod configuration activated a design characteristic that was known to reactor specialists but had been considered a minor operational nuisance rather than a fundamental safety concern. With control rods withdrawn to upper limits, water columns approximately 1.25 meters high occupied the space below each graphite displacer in the fuel channels. When rods began inserting from this position, the graphite displacers would initially move downward into these water columns, displacing water with graphite that absorbed significantly fewer neutrons. The neutron physics of this displacement were straightforward but had profound implications for reactivity balance. Water has a much larger neutron absorption cross-section than graphite, meaning that replacing water with graphite in the lower portion of fuel channels would allow more neutrons to cause fission rather than being absorbed unproductively. This effect would introduce positive reactivity into the reactor core precisely when the emergency protection system was intended to provide maximum negative reactivity. Soviet reactor designers were aware of this phenomenon, which they termed the end rods effect, or positive reactivity surge. Internal documentation from the chief designer organization acknowledged that control rod insertion from fully withdrawn positions could temporarily increase reactivity before the absorber sections reached the fuel region and began providing negative reactivity. However, their understanding of when and under what conditions this effect would manifest remained incomplete and was based on analytical methods that could not capture the full complexity of spatial neutronics under transient conditions. The magnitude of positive reactivity insertion from graphite displacer displacement depended critically on the reactor's existing configuration. Under normal operating conditions with adequate control rod insertion distributed throughout the core, the positive reactivity from displacer movement would be small and would be quickly overcome as absorber sections reach the fuel region. However, under the current conditions with minimal existing rod insertion and enhanced void coefficients, the positive reactivity surge could be much larger and longer lasting. As the control rods began their descent at 1:23:40, the graphite displacers started displacing water from the bottom of fuel channels throughout the core. Within the first 2 seconds of rod movement, this displacement had introduced approximately 1 to 2 beta-F of positive reactivity into the lower core region, equivalent to the total delayed neutron fraction that normally provided time for control system response. This reactivity insertion occurred faster than any control system could compensate and exceeded the remaining control authority available with most rods already withdrawn. The spatial distribution of this positive reactivity insertion created additional complications that amplified its effect. Because the reactor operated at low power with distorted flux distribution, the neutron population was concentrated in core regions where control rod effectiveness was minimal. The positive reactivity introduced by graphite displacer insertion occurred precisely in these already active regions, creating localized power increases that could not be controlled by the few rods that remained available for compensation. Neutron monitoring systems throughout the core began registering rapidly increasing flux levels as the positive reactivity insertion took effect. The reactor period shortened dramatically, dropping from minutes to seconds as power began increasing exponentially rather than decreasing as expected from emergency shutdown activation. Local power monitors in the lower core region showed flux increases that quickly exceeded their measurement ranges, indicating power levels far beyond normal operating envelopes. The rapid power increase created immediate thermal effects that initiated positive feedback loops throughout the reactor core. As power increased, fuel temperatures rose rapidly, heating coolant water and creating additional steam void formation. The increased voiding introduced additional positive reactivity through the void coefficient, further accelerating the power increase. Each increment of power increase created conditions that promoted additional power increases, establishing an accelerating cycle that quickly moved beyond any possibility of control. Within approximately 4 seconds of AZ-5 activation, several control rods had moved far enough into the core for their absorber sections to begin providing negative reactivity. However, the positive reactivity already inserted by graphite displacement, amplified by void formation and spatial coupling effects, had created a power excursion that overwhelmed this negative reactivity contribution. The reactor power increased by factors of 10, then 100, reaching levels that exceeded the design capability of fuel assemblies to maintain their geometry. As fuel temperatures reached and exceeded the melting point of uranium dioxide, the carefully engineered geometry that enabled controlled nuclear reactions began to disintegrate. Fuel pellets began fragmenting and relocating within fuel rods, disrupting the precise spacing required for controlled neutron moderation. Steam formation became so rapid that fuel channel walls experienced pressure loadings far exceeding their design capability. The zirconium cladding that provided the first barrier against fission product release began failing through a combination of thermal and mechanical stress. The failure of fuel geometry created additional reactivity effects that further accelerated the destruction process. As fuel relocated and channels began deforming, neutron moderation characteristics changed in ways that generally increased reactivity rather than providing the negative feedback that might have limited the excursion. The carefully designed neutron economy that made RBMKs efficient during normal operation became a liability during accident conditions, with each geometric change promoting additional power increases. Simultaneously, the rapid steam generation created pressure waves that propagated throughout the reactor coolant system. Individual fuel channels began experiencing pressures that exceeded the capacity of their zirconium walls to contain primary coolant. Channel ruptures began occurring throughout the core, releasing highly radioactive steam and water into the reactor space surrounding the graphite moderator. These ruptures eliminated cooling from affected fuel assemblies while creating additional void space that further increased reactivity. The rate of energy release during this phase exceeded anything considered credible in reactor design analyses. Power levels reached an estimated 100 times normal reactor power within a few seconds, creating energy deposition rates that vaporized coolant faster than it could be supplied, and raised fuel temperatures to levels where chemical reactions between zirconium cladding and steam began generating hydrogen gas. The controlled nuclear reaction had become an uncontrolled energy release that was destroying the reactor faster than any protective system could respond. As fuel channel integrity collapsed throughout the core, the reactor's coolant inventory began escaping into the reactor cavity, creating the conditions for steam explosion. The interaction between extremely hot fuel debris and the remaining coolant water created rapid steam generation at pressures far exceeding the design capability of the reactor building structures. The first explosion, occurring approximately 6 to 7 seconds after AZ-5 activation, represented this steam explosion as supercritical fuel fragments contacted large quantities of coolant water. However, physical evidence and subsequent analysis suggest that the steam explosion was followed by an even more destructive nuclear explosion. The rapid disassembly of fuel geometry and expulsion of coolant had created conditions where the remaining fuel could achieve supercritical mass configurations that were impossible under normal reactor conditions. Unlike controlled nuclear reactions moderated by water and regulated by control rods, this supercritical assembly would release energy in the manner of a nuclear weapon, though with much lower efficiency. The evidence for nuclear explosion includes the specific isotopic signatures found in environmental samples following the accident. Analysis of xenon-133 and xenon-133m ratios in air samples collected at distances up to 1,000 kilometers from Chernobyl showed proportions consistent with nuclear explosive yields rather than normal reactor operation or steam explosion alone. The energy release required to destroy reactor building structures and eject reactor components over vast distances also exceeded what could be explained by steam explosion mechanisms. The nuclear explosion represented the final phase of a failure sequence that had begun with the positive reactivity insertion from control rod graphite displacers and escalated through positive feedback loops that overwhelmed all protective systems. The total energy release has been estimated at equivalent to approximately 200 tons of TNT, a yield that no containment system could withstand and far exceeding any accident scenario considered in reactor design. The destruction was essentially instantaneous once critical thresholds were crossed. The control rods that were supposed to guarantee reactor safety had instead initiated a sequence of physical processes that led inevitably to reactor destruction. The emergency protection system had become the triggering mechanism for the very accident it was designed to prevent. The reactor that had operated safely for years, under a wide variety of conditions, had been destroyed by the activation of its own safety systems. This contradiction between design intent and actual performance represented more than simply an engineering failure. It demonstrated how complex technical systems can contain failure modes that are invisible under normal operating conditions, but become active when specific boundary conditions are encountered. The emergency protection system had been tested and validated under a wide range of conditions, but never under the specific combination of low power, minimal rod insertion, and enhanced void coefficients that existed during the test. The failure sequence also illustrated how multiple safety systems could fail simultaneously when they shared common vulnerabilities. The reactor physics that made the positive reactivity surge possible also made the automatic control systems ineffective and eliminated the negative feedback mechanisms that normally provided inherent stability. A single design characteristic, the graphite displacer configuration, created a common mode failure that defeated multiple independent protective systems. Perhaps most significantly, the physics of the failure sequence made recovery impossible once the positive reactivity surge began. Unlike many industrial accidents where prompt recognition and response can limit consequences, the Chernobyl accident involved physical processes that occurred too rapidly for any human or automatic response. Once the control rods began moving and positive reactivity insertion started, the subsequent power excursion and fuel destruction followed from fundamental physics laws that could not be altered by any available intervention. The 4 seconds between AZ-5 activation and reactor destruction represented not a period when different decisions might have changed outcomes, but rather the time required for physical processes to play out according to the reactor configuration that had been established over the preceding hours. The accident was determined not by actions taken during the emergency, but by the conditions that existed when the emergency response was initiated. The explosions that destroyed Chernobyl Unit 4 at 1:24 on April 26, 1986, marked not the end of the nuclear emergency but the beginning of a new phase of crisis management that would continue for months. The initial destruction had eliminated the primary containment barriers and dispersed radioactive material across a wide area, but significant quantities of fuel and graphite remained within the destroyed reactor structure, creating ongoing hazards that required immediate response despite extreme radiation levels and physical destruction. The first indication that catastrophic destruction had occurred came from seismic monitoring stations that detected the explosive events, followed by radiation alarms throughout the plant site. However, the scope of destruction was not immediately apparent to plant personnel or emergency responders. The reactor building's external walls remained largely intact, concealing the complete destruction of internal structures and the reactor itself. Initial reports from the scene described a serious accident with possible fuel damage, not the complete reactor destruction and massive radiological release that had actually occurred. This initial misunderstanding of accident severity reflected both the unprecedented nature of the event and the limitations of emergency assessment systems available in 1986. No previous reactor accident had involved complete core destruction and building breach, leaving emergency responders without relevant experience or procedures for assessing such extreme conditions. Radiation monitoring systems designed for normal accident response were overwhelmed by dose rates that exceeded their measurement capabilities, providing little useful information about the actual radiological situation. Plant management's initial assessment focused on possibilities that seemed credible based on previous nuclear experience: partial fuel damage, coolant system ruptures, or steam explosions that might have damaged reactor internals while leaving basic structures intact. The concept that an entire reactor core could be destroyed and dispersed was outside the envelope of considered possibilities, leading to response strategies that were inadequate for the actual situation. The first emergency response teams entered the reactor building expecting to find damaged but recognizable systems that could potentially be restored to safe conditions. Instead, they encountered complete destruction of familiar plant areas, radiation levels that immediately incapacitated personnel despite protective equipment, and physical conditions that made normal emergency procedures impossible to implement. The reactor hall, which should have contained the upper biological shield and refueling equipment, was filled with debris and radioactive graphite blocks that had been ejected from the destroyed core. Attempts to provide emergency cooling to the reactor quickly proved futile as the systems designed for this purpose no longer existed. The emergency core cooling system that had been disabled for the turbo generator test could not have functioned even if restored, as the fuel channels and coolant flow paths had been completely destroyed. Water pumped toward the reactor cavity simply drained away through damaged structures, carrying dissolved radioactive materials toward lower building levels and eventually into groundwater systems. The destroyed reactor presented multiple simultaneous hazards that challenged all conventional emergency response approaches. The remaining fuel and graphite continued to generate significant decay heat that could not be removed through normal cooling systems. Approximately 1,700 tons of graphite moderator had been exposed to air at temperatures high enough to sustain combustion, creating a massive radioactive fire that released fission products directly to the atmosphere. The destroyed reactor building provided minimal containment for these releases, allowing radioactive materials to disperse widely through atmospheric transport. Fire suppression efforts faced unique challenges that conventional firefighting equipment and procedures could not address effectively. Water applied to the graphite fire created steam that enhanced the transport of radioactive materials into the atmosphere while doing little to extinguish the graphite combustion. The graphite burned at temperatures exceeding 700 degrees Celsius, well above the ignition temperature for sustained combustion in air, and the massive quantity of material meant that the fire would continue until either the oxygen supply was eliminated or the combustible material was exhausted. Initial attempts by plant firefighters and local emergency services to suppress the fires using conventional methods proved both ineffective and extremely hazardous to personnel. Firefighters approaching the reactor building received lethal radiation doses within minutes of exposure, yet the scale of visible destruction was not initially recognized as indicating complete reactor loss. Many early responders suffered acute radiation sickness that was not immediately diagnosed, as medical facilities had limited experience with such extreme radiation exposures. The graphite fire created its own meteorological effects that complicated atmospheric dispersion predictions and emergency response planning. The intense heat generated strong convection currents that lifted radioactive particles high into the atmosphere, where they could be transported hundreds of kilometers before deposition. The thermal effects also created local wind patterns that could shift dispersion directions unpredictably, making it difficult to establish safe evacuation zones or predict which areas would receive significant contamination. Attempts to extinguish the graphite fire through aerial drops of various materials reflected the desperation of responders facing an unprecedented emergency. Helicopter crews delivered thousands of tons of sand, clay, lead, and boron compounds in efforts to smother the combustion and provide additional neutron absorption in case remaining fuel achieved critical configurations. However, most of this material missed the target area due to intense thermal updrafts and radiation effects on helicopter operations, while material that did reach the fire often enhanced rather than suppressed the combustion by providing additional thermal mass. The boron compounds dropped from helicopters were intended to prevent renewed criticality in fuel that remained within the reactor cavity. Theoretical analyses suggested that if sufficient fuel collected in optimal configurations with appropriate moderation, renewed fission chain reactions could occur, potentially leading to additional power excursions. However, the physical condition of the destroyed fuel made such scenarios highly unlikely, as the precise geometry required for sustained criticality had been thoroughly disrupted by the initial explosions. More immediate concerns involved the potential for secondary explosions that could further disperse radioactive material or damage adjacent reactor units. Hydrogen gas generated from metal-water reactions during the initial accident had accumulated in various building spaces, creating explosion hazards that persisted for days after the initial event. Additionally, concerns arose about steam explosions that could occur if the remaining hot fuel contacted large quantities of water, potentially breaching lower containment barriers and contaminating groundwater supplies. The decision to flood lower reactor building levels with water to prevent potential steam explosions created new complications for long-term stabilization efforts. While successful in preventing feared secondary explosions, the water became highly contaminated as it contacted radioactive debris and began creating pathways for contamination to reach groundwater systems. This contaminated water would later require extensive treatment and storage, creating ongoing environmental hazards that persisted long after the immediate fire dangers were controlled. Assessment of radiation release rates proved extremely difficult due to the destruction of normal monitoring systems and the unprecedented scale of the accident. Dose rate measurements near the reactor showed readings that exceeded the range of available instruments, while atmospheric monitoring detected radioactive plumes that extended far beyond plant boundaries. The lack of precedent for such releases made it difficult to predict dispersion patterns or assess potential health impacts on surrounding populations. The decision to evacuate nearby communities reflected growing recognition that the accident involved much more severe consequences than initially assessed. The evacuation of Pripyat, beginning approximately 36 hours after the accident, marked acknowledgement that normal emergency response measures were insufficient and that the radiological release posed significant risks to public health. However, even this evacuation was initially conceived as a temporary measure, with residents told they would return within days once the situation was stabilized. International detection of radioactive releases provided the first objective confirmation of the accident's severity. Radiation monitoring stations in Sweden, Finland, and other European countries detected atmospheric contamination patterns that indicated a major nuclear accident somewhere in the Soviet Union. These detections occurred before Soviet authorities had publicly acknowledged the severity of the event, creating diplomatic complications that further delayed effective international assistance. The graphite fire continued for approximately 10 days, gradually diminishing as combustible material was consumed and oxygen access became limited by debris accumulation. The end of visible fire marked a transition from acute emergency response to longer-term stabilization efforts, but significant radioactive releases continued through other mechanisms, including dust dispersion from contaminated surfaces and continued volatilization of fission products from hot fuel debris. Stabilization of the destroyed reactor required unprecedented engineering solutions for containing and managing radioactive materials under extreme conditions. The construction of the sarcophagus structure over the destroyed reactor building represented one of the largest civil engineering projects ever undertaken under high radiation conditions, requiring remote construction techniques and radiation shielding methods that had never been attempted on such a scale. The sarcophagus design reflected compromises between ideal containment objectives and practical constraints imposed by radiation levels, structural damage, and time pressures. The structure was intended to limit further atmospheric releases and provide weather protection for remaining radioactive materials, but it could not provide the complete isolation that would be required for permanent disposal. The design acknowledged that the sarcophagus was a temporary measure that would require replacement or major modification within decades. Long-term monitoring revealed that stabilization efforts had been only partially successful in controlling ongoing releases and environmental contamination. Radioactive materials continued to migrate through groundwater systems, atmospheric releases persisted at low levels for years, and the structural integrity of hastily constructed containment barriers remained uncertain. The destroyed reactor had been stabilized in the sense that catastrophic additional releases were prevented, but it remained a significant environmental hazard requiring ongoing management. The secondary crises that emerged during stabilization efforts demonstrated how nuclear accidents can create cascading effects that persist long after initial emergency conditions are controlled. Contaminated water treatment, radioactive waste storage, health monitoring for exposed personnel, agricultural restrictions, and environmental remediation created ongoing challenges that continued for decades. The accident had created not just immediate destruction, but a contaminated zone requiring permanent monitoring and restricted access. Perhaps most significantly, the stabilization experience revealed limitations in emergency preparedness that extended beyond technical systems to encompass organizational, political, and international coordination mechanisms. The unprecedented nature of the accident overwhelmed existing emergency response frameworks, requiring improvised solutions that often proved inadequate for the scale and duration of required response efforts. The accident demonstrated that severe nuclear emergencies could create problems that exceeded the capabilities of normal emergency response organizations and required fundamentally different approaches to crisis management. The physical evidence recovered from the destroyed Chernobyl Unit 4 reactor provided definitive proof that the accident had resulted from fundamental design characteristics rather than operator error, contradicting initial Soviet explanations that had blamed the disaster on procedural violations. Forensic analysis of reactor debris, isotopic measurements, and structural damage patterns revealed the sequence of physical events that had destroyed the reactor, while subsequent investigations by international experts established the systemic factors that had made such destruction possible. The most compelling forensic evidence came from isotopic analysis of atmospheric samples collected at monitoring stations throughout Europe in the days following the accident. Soviet scientists Pakhomov, Krivokvatsky, and Sokolov analyzed xenon-133 and xenon-133m ratios in air samples collected as far as 1,000 kilometers from Chernobyl, finding proportions that matched those expected from nuclear explosive yields, rather than normal reactor operation or steam explosion alone. The xenon isotope ratios provided a distinctive signature that could only result from the extremely high neutron fluxes characteristic of nuclear explosions. This isotopic evidence supported theoretical calculations suggesting that the energy released during reactor destruction had exceeded 200 tons of TNT equivalent, far beyond what steam explosion mechanisms could explain. The nuclear explosion hypothesis also accounted for physical observations that were otherwise difficult to explain, including the blue flash witnessed by plant personnel and the massive energy required to eject reactor components over distances of several hundred meters. Physical inspection of the destroyed reactor cavity, conducted by remote camera systems and robotic equipment due to extreme radiation levels, revealed that virtually no recognizable reactor components remained in their original positions. The reactor vault that should have contained the graphite moderator stack and fuel channels was essentially empty, with only scattered debris indicating the former presence of massive structural components. The complete absence of large reactor components from their designed locations provided physical confirmation that explosive forces had been sufficient to disperse the entire reactor core. The upper biological shield, a 2,000-ton concrete and steel structure that covered the reactor core, had been lifted vertically and tilted at approximately 15 degrees from its original position. The energy required to move this massive structure indicated explosive forces that exceeded any credible steam explosion scenario. Analysis of the shield's final position and the pattern of surrounding debris provided insights into the direction and magnitude of forces generated during the destruction sequence. Structural analysis of reactor building damage revealed patterns consistent with internal explosive forces originating from the reactor core region. The reactor hull ceiling had been completely destroyed, with debris patterns indicating upward-directed forces that had torn through multiple structural layers. However, the external walls of the reactor building remained largely intact, suggesting that the explosive forces had been channeled primarily upward through the reactor hull rather than laterally through containment barriers. The distribution of radioactive debris across the plant site provided additional forensic evidence about the explosion sequence and energy release. Large graphite blocks from the reactor moderator were found at distances exceeding 600 meters from the reactor building, indicating ejection velocities that required extremely high explosive forces. Fuel fragments were discovered throughout the plant site, with some pieces showing evidence of having been molten during the explosion sequence before solidifying in their current locations. Analysis of fuel fragment composition revealed important details about reactor conditions immediately before destruction. Isotopic analysis showed that fuel from different core regions had been mixed during the explosion, indicating that the destruction process had completely disrupted normal fuel geometry. Some fragments contained evidence of extremely high temperatures that could only have been achieved during the brief period of supercritical energy release, supporting the nuclear explosion hypothesis. The pattern of radioactive contamination around the plant site also provided insights into the explosion sequence and atmospheric release mechanisms. Contamination surveys showed distinct directional patterns that correlated with meteorological conditions during and immediately after the accident. The heaviest contamination occurred in areas downwind from the reactor at the time of destruction, while lighter contamination extended much further due to the high altitude reached by the radioactive plume. International investigation teams that gained access to Soviet data several years after the accident found significant discrepancies between initial official explanations and documented evidence. The State Committee for Atomic Safety Survey of the USSR, led by Nikolai Steinberg, concluded in 1991 that design deficiencies rather than operator errors had been the primary cause of the accident. This conclusion directly contradicted the explanation provided to the International Atomic Energy Agency in 1986, which had attributed the accident primarily to procedural violations. The Steinberg Commission's investigation revealed that Soviet experts had initially misunderstood fundamental aspects of their own reactor design. Internal documents showed that the chief designer organization had not fully analyzed the positive reactivity effects of control rod insertion from fully withdrawn positions, leading to emergency procedures that were actually dangerous under specific reactor conditions. The investigation found that operators had generally followed approved procedures and that their actions had been reasonable given the information available to them. International review of the accident through the IAEA's INSAG process led to a fundamental revision of the accident's causes and lessons. INSAG 1, published in 1986, had largely accepted Soviet explanations that emphasized operator error and procedural violations. However, INSAG 7, published in 1992 after more complete information became available, concluded that design deficiencies were the primary contributing factors and that operator actions had played a secondary role. The revised international assessment identified specific design features that had made the accident possible: the positive void coefficient under certain operating conditions, the positive reactivity effect of control rod insertion from fully withdrawn positions, insufficient control rod insertion speed, and inadequate reactor cavity overpressure protection. These design characteristics created the potential for accident sequences that could not be controlled by operator actions or existing safety systems. The forensic analysis also revealed significant deficiencies in the Soviet nuclear regulatory system that had allowed dangerous reactor designs to remain in operation, despite evidence of serious safety problems. Internal Soviet documents showed that safety concerns about RBMK reactors had been raised repeatedly by specialists within the nuclear program. But organizational and economic factors had prevented implementation of necessary modifications. Evidence emerged that similar reactivity excursions had occurred at other RBMK reactors prior to Chernobyl, including incidents at Leningrad Unit 1 in 1975 and Chernobyl Unit 1 in 1982. These earlier events had involved partial fuel damage due to positive reactivity effects, but had not escalated to full-scale destruction due to different initial conditions. However, the lessons from these incidents had not been systematically analyzed or incorporated into reactor design modifications. The investigation revealed that economic considerations had played a significant role in delaying safety improvements that could have prevented the Chernobyl accident. Modifications needed to eliminate the positive void coefficient, including additional control rods and higher fuel enrichment, were technically feasible, but would have significantly increased operating costs. Soviet planners had chosen to defer these improvements in favor of maintaining the economic advantages that made RBMK reactors competitive with other power sources. International analysis of the accident's causes led to fundamental changes in nuclear safety philosophy and regulation worldwide. The accident demonstrated that design basis accidents could be exceeded by event sequences that had not been adequately analyzed, leading to requirements for more comprehensive safety analysis, including severe accident scenarios. The importance of defense in depth through multiple independent safety systems was reinforced, with particular emphasis on passive safety features that did not depend on operator actions or active systems. The accident also highlighted the importance of international cooperation and information sharing in nuclear safety. The initial Soviet secrecy about the accident's causes had prevented other countries from learning important safety lessons, while the eventual international investigation provided benefits that no single country could have achieved independently. This experience led to enhanced international frameworks for nuclear emergency response and safety information exchange. Human factors analysis of the accident revealed fundamental problems with control room design and operator training that extended beyond the specific case of RBMK reactors. The accident demonstrated how operators could make reasonable decisions based on available information, yet still contribute to dangerous situations due to inadequate instrumentation or training. This analysis led to improved human factors engineering requirements for new reactor designs and enhanced training programs that emphasized understanding of underlying safety principles rather than rote procedural compliance. The long-term environmental and health consequences of the accident provided additional evidence about the magnitude of radioactive releases and their distribution patterns. Detailed contamination surveys revealed that significant areas of Ukraine, Belarus, and Russia had received contamination levels that required agricultural restrictions and population relocations. The environmental monitoring data confirmed that the accident had involved massive releases of radioactive materials over an extended period, contradicting initial Soviet claims of limited environmental impact. Health studies of exposed populations provided insights into radiation effects that had not been well understood from previous nuclear weapons testing or industrial exposures. The accident created a unique opportunity to study health effects in large populations exposed to varying levels of radioactive contamination over extended periods. While the health consequences remain subjects of scientific debate, the studies have contributed significantly to understanding of radiation health effects at relatively low exposure levels. The economic consequences of the accident provided quantitative evidence of the costs associated with inadequate nuclear safety. Direct costs of emergency response, environmental remediation, healthcare, and economic displacement exceeded tens of billions of dollars, while indirect costs from lost agricultural production, tourism impacts, and energy system disruption extended the total economic impact even further. These costs demonstrated that investing in enhanced safety systems was economically justified even for very low probability events. Perhaps most significantly, The forensic evidence and subsequent analysis established that the Chernobyl accident represented a predictable consequence of specific design and organizational characteristics rather than an unforeseeable combination of random events. The accident demonstrated how apparently reasonable engineering compromises and organizational pressures could combine to create systems that appeared safe under normal conditions but contained latent failure modes that could be activated under specific boundary conditions. The comprehensive investigation of the Chernobyl accident established new standards for nuclear safety analysis that extended far beyond reactor physics to encompass human factors, organizational influences, and regulatory effectiveness. The forensic evidence provided definitive proof that nuclear safety required attention to system-level interactions rather than individual component performance, and that apparent compliance with existing standards could be insufficient to prevent accidents under conditions that had not been adequately analyzed. The legacy of Chernobyl's forensic analysis continues to influence nuclear safety practices decades after the accident. The investigation demonstrated the importance of rigorous safety analysis, conservative design practices, and organizational cultures that prioritize safety over production goals. Most importantly, the forensic evidence showed that complex technical systems can fail in ways that exceed the imagination of their designers, requiring safety approaches that account for uncertainty and incomplete understanding, rather than assuming that all important failure modes have been identified and controlled.